Now our next chapter is alkanes and cycloalkanes. Alkanes introduction. Organic compounds containing only carbon and hydrogen are called hydrocarbons. These are broadly divided into two categories: open chain or acyclic hydrocarbons and closed chain. Second is closed chain or chain cyclic hydrocarbons. The open chain or acyclic hydrocarbons are also called aliphatic hydrocarbons. They can be further divided into two categories: alkanes, into three categories: alkanes, alkenes, and alkynes. Alkanes are saturated acyclic hydrocarbons having the general formula CnH2n plus 2, where n can be an integer. As such, they contain only carbon-carbon and carbon-hydrogen bond, single bond, so they are relatively inert towards most of the chemical reagents, so they are also called paraffins. In contrast, cyclic compounds corresponding to alkanes or paraffins are called cycloalkanes or cycloparaffins. The general formula is CnH2n, where n is equals to 3, 4, etc. In this unit, we shall discuss the nomenclature, method of preparation, and the properties of alkanes. First, we will do nomenclature of alkanes. The common and IUPAC name of simple alkanes are discussed below. General formula CnH2n plus 2, where n is equals to any integer, that is 1, 2, 3, 4 up to infinity. They are also represented as RH, where R is equals to CnH2n plus 1 is an alkyl group. Common and IUPAC name. The first four members of homologous series are known by their special names, that is methane, ethane, propane, and butane, while the higher members are prefixing the Greek numeral pent for 5, 6, for hex, hept for 7, oct for 8, are indicated as number of carbons atom in the molecules to the suffix "ane". The name of individual alkane is written as one word root as shown in below. Second, types of alkene. Depending upon the structure of the carbon chain, alkanes are of following two types: straight chain alkanes and second branch chain alkane. First, we will discuss about straight chain alkanes. As the name suggests, these alkanes contain only chains of carbon atoms in their molecules. In other words, alkenes in which no carbon atom is linked to more than two other carbon atoms are called straight chain alkenes. Example: butane, hexane, n-hexane, and butane. The common name of straight chain alkanes are the same as their IUPAC name, except the prefix n. N is used for normal, is used in the common names, which is given in the brackets. Second is branched chain alkanes. In these alkanes, all the carbon atoms are not present in a linear sequence. In other words, alkanes in which at least one carbon atom is linked to 3 or 4 other carbon atoms are called branched chain alkanes. For example, isobutane, isopentane, isohexane, neopentane, neohexane. To distinguish the straight chain alkanes from branched chain alkanes of same molecular formula, the prefix iso and neo are used in the common system. The prefix iso is used when the second carbon of the branched chain alkane carries one methyl group, while the prefix neo is used when the second carbon atom of the branched chain alkane contains two methyl groups. Next, classification of carbon atoms. The carbon atoms in an alkane molecules may be classified into four types as primary, secondary, tertiary, and quaternaries as follows. The hydrogen atom attached to primary, secondary, and tertiary atoms are called primary, secondary, and tertiary hydrogen atoms. It may be here noted that there is nothing like quaternary hydrogen atom, since a quaternary carbon does not carry any hydrogen. Next, nomenclature of alkyl groups. The removal of one hydrogen atom from the molecule of an alkane gives the corresponding alkyl group. General formula CnH2n plus 1 or R. Common names, they are obtained by replacing the terminal "ane" of the corresponding alkane by the suffix "-il", so its name is alkyl. IUPAC names. Common names of the simple alkyl groups are also written in the IUPAC system. But quite often in the IUPAC system, the branched chain alkyl groups are named as an alkyl derivative of the corresponding chain alkanes. The common and IUPAC name of some alkyl groups are given below. CH3, common name methyl, and IUPAC name is also methyl. C2H5, common name and methyl is common name and IUPAC name is both the ethyl. For IUPAC name and common name is N-propyl for the propane if one H is removed from that group. Similarly, 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 we can calculate for all the groups. Next, we will do nomenclature of branched chain alkanes. The IUPAC names of the branched chain or complex alkanes are derived according to the following rules. First, longest chain rule. Select the longest chain, continuous chain of carbon atoms in a molecule. This is called the parent chain, while the other carbon atoms which are not inclined in the parent chain are regarded as prefix, that is side chain or substituent. The complex alkane is then named as a derivative of the alkane representing the parent chain. It may be noted that the longest chain must always be continuous. It may or may not be straight. Second rule for largest number of side chains. If two different chains of equal length are possible, select the one with larger number of side chains or alkyl groups. Third, lowest number rule or lowest loctant rule. A. Number the carbon atom of the parent chain as 1, 2, 3, 4, etc. starting from the end, which gives the lowest possible numbers to the carbon atom carrying the substituent. For example, in structure 1, the numbering can be done in two different ways, 1A and 1B. The numbering of carbon chain is assigned in structure 1A is correct since it assigns a lower number 3 to the methyl substituent, while the numbering as given in structure 1B is wrong since it assigns a higher number 4 to the methyl substituent. The number that indicates the position of the substituent on the parent chain is called positional number or loctant. Thus, the correct loctant for the methyl side chain is in structure 1A, that is 3. B. Loctant sum lowest set of loctant rule. When two or more substituents are present, the carbon atom of the parent chain are numbered in such a way that the set of loctants is the lowest. This is called lowest set of loctant rule. For deciding the lowest set of loctants, the carbon atom of the parent chain are numbered from all the possible directions and a loctant assigned to each substituent from either direction. The set of loctants from either direction are then compared term by term till the first point of difference is reached. The set of loctants is preferred which has a lower number at the first point of the difference. That is why this rule is sometimes called as a first point of difference. In accordance with the above rules, the carbon atom of A of the alkanes given below should be numbered as shown in the figure A and not in the figure B. Next is name of the complex alkene. Prefix the name of the substituent by writing before it the number of the carbon atom carrying the substituent. The name of the substituent is separated from its loctant by a hyphen. The final name of the alkene is always written as one word. Some examples are given below for this illustration. 2-methyl butane, 3-ethyl hexane are the examples of this. Next is alphabetically order of the simple substituent. When two or more simple substituent groups are present on the parent chain, each alkyl group prefixed by its loctant is arranged in alphabetically order irrespective of its locant before the name of the parent alkene. For example, 3-ethyl 2-methylhexane or 4-ethyl 3-methylheptane. It may be noted here that while deciding the alphabetically order of the various alkyl groups, prefix iso and neo are considered to be the part of the fundamental name of the alkyl group, while the prefix secondary and tertiary are not. For example, 5 secondary butyl 4 isopropyldecane, 4 tertiary butyl 3 ethyl 2 8 dimethyl 6 neopentaldecane. Next is numbering of the different substituent at equivalent position. When two different substituents are present on the equivalent position, the numbering of the parent chain is done in such a way that the substituent which comes first in alphabetically order gets the lowest number. Example is 3-ethyl 5-methyl heptane. Next is naming same substituent at different position. When the same substituent occurs more than one on the parent chain at different position, the loctant of each substituent is separated by commas and suitable numerical prefix such as dia42, tria43, tetra44, etc. are attached to the name of the substituent. However, the prefix dia, tri, etc. are not considered while deciding the alphabetical order of the alkyl group. The example is 2,2-dimethyl-propane, 2,2,4-trimethylpentane, 2,5,6-trimethyloctane, etc. are the examples of this. Eighth is naming the complex substituent. In case the substituent on the parent chain is complex, it is named as a substituted alkyl group by separately numbering the carbon atom of this group attached to the parent chain as one. The name of such a substituent is always enclosed in bracket to avoid confusion with the number of the parent chain alkene. For example, 5 hyphen bracket start 2 dimethyl propyl bracket close none. Second, if the chain length of two complex substituent is of equal length, then the complex substituted with larger number of alkyl groups forms a part of the longest chain, while the other one is considered the real complex. For example, 5 2 ethyl butyl bracket close hyphen 3 3 dimethylnonane. C is while deciding the alphabetical order of the various substituent, the name of the complex substituent is considered to begin with the first letter of its complex name. It may be here noted that dimethylbutyl group as a complete substituent is alpha betized under D and as such is cited force E of the ethyl group. Last is when the name of the two or more substituents are composed of identical words, priority of the citation is given to that substituent which has the lowest loctant at the first stated point of difference within the complex substituent. For example, 6,1 methyl butyl 8 2 methyl methyl octane. It may be here noted that 1 methyl butane group is a given priority of citation over 2 methyl butyl group because its loctant is 1 comes before. Next is sources of alkanes. Petroleum and natural gases are the two important principal sources of alkane. Methane is also the principal constituent of the marsh gas produced by the anaerobic fermentation of cellulose. Some plant waxes also contain alkanes. For example, wood, turpentine, or some pine trees contain N-heptane, and cabbage leaves contain N-nona-oxane. Formula for N-nona-oxane is C29H60. Next is general method of preparation of alkanes. First is catalytic hydrogenation of unsaturated hydrocarbons. The addition of hydrogens to unsaturated hydrocarbons, such an alkene or alkyne, to form alkanes is called hydrogenation. It is usually carried out by treating the unsaturated compound with molecular hydrogen in presence of finely divided metal catalyst such as platinum, palladium, nickel, etc. While platinum, palladium, and nickel hydrogenation proceeds smoothly and quantitatively at ordinary temperatures and pressures. However, with ordinary nickel as catalyst, relatively higher temperatures are like 523 to 573 Kelvin are often required. The hydrogenation of an unsaturated hydrocarbon using ordinary nickel at a temperature of about 523 to 573 Kelvin is commonly known as Savatier's inverse reaction or reduction. Catalytic hydrogenation is by the far most important method of preparation of alkanes. However, methane can't be prepared by this method. Second is reduction of alkyl halide. Alkyl halides can be reduced to alkanes by a number of different reagents, either directly or indirectly. A direct reaction of alkyl halides may be done in following ways. First, reduction by dissolving metals such as zinc, NCH3COH or HCl, Zn and NaOH or ZnCu couple and ethanol etc. use. Mechanism. The reduction occurs by the transfer of electrons from the metal to the alkyl halide forming first carboanion which being highly reactive then abstract a proton from the acid or any potential proton donor such as alcohol which is shown in the bill. Second is reduction by chemical reagents such as lithium aluminum hydride and sodium borohydride NaBH4. Primary and secondary alkyl halides are readily reduced to alkanes by lithium aluminum hydride, but tertiary halide mainly undergo dehydrogenation to give alkenes. On the other hand, NaBH4 reduces secondary and tertiary alkyl halide but not primary, whereas tryptolanium reduces all the three parts of the alkyl halides. Next is catalytic hydrogenation. Implies cleavage of sigma bond with H2 in the presence of catalyst. The best catalyst for platinum nickel is platinum carbon, but Rene nickel has also been effective provided it is used in the large accretion. Reduction with next is reduction with HI and red phosphorus. Alkyl hydrates are readily reduced to the corresponding alkanes by heating with concentrated HI in the presence of red phosphorus at 423. Ri plus HI is equal in the presence of red phosphorus at the temperature of 423 Kelvin is RH plus I2. The purpose of red phosphorus is to remove the iodine liberated in the reaction. Otherwise, it would react with the alkane to give the corresponding alkyl halide back. Second is indirect reaction. Alkyl halides react with the magnesium and triether to form alkyl magnesium halide called Grignard reagent. These Grignard reagents are very reactive and hence are decomposed by water or any potential proton donors such as alcohols, amines, etc. to form alkanes. The order of reactivity of different alkyl halides in this reaction follow the sequence iodides, bromides, chlorides. Alkyl fluoride, however, do not react. This method is quite convenient for the preparation of symmetrical alkanes, that is, alkanes containing even number of carbon atoms such as ethane and butane, hexane, octane, decane, etc. However, it is not suitable for the preparation of unsymmetrical alkanes, that is, alkanes containing odd number of carbon atoms such as propane, pentane, heptane, nonane, etc. This is because of the reason that in the preparation of such alkanes, an equimolar mixture of two different alkyl halides is used. In addition to the reaction with each other, so also amongst themselves producing a mixture of three alkanes. For example, when a mixture of methyl bromide and ethyl bromide is treated with sodium, it forms a mixture of ethane and butane and propane according to the reactions first, second, and third respectively as shown in the figure. Limitations. Halogen compounds containing other reactive functional groups such as OH, carboxylic acid, etc. cannot be used in this reaction. The reaction fails with tert alkyl halides. Methane can't be prepared by this method. Importance. Woods reaction is a very useful for ascending the series of organic compounds since it involves the mechanism since it involves the formation of new carbon bond. Free radical mechanism. The mechanism operates when the reaction is carried out in vapor phase. Sodium first reacts with alkyl halide forming free radicals which then couple together to form alkenes. Next is Core-House reaction. This is a very useful variation of Wood's reaction and involves the interaction between a suitable lithium dicuprate with an alkyl halide to form alkane in an excellent yields. Lithium dicuprate needed for the purposes as follows. For good yields, alkyl halide must be either a methyl halide, a primary alkyl halide, or a secondary cycloalkyl halide with the while the alkyl group in organometallical compounds may be methyl, primary, secondary, and tertiary. Merits. Core-House reaction is better than Wood's reaction since it can be used for the synthesis of all types of alkanes, which may be straight chain or branched chain and may contain either even an odd number of carbon atoms. This reaction is particularly used for the synthesis of higher alkanes. Fifth is decarboxylation of carboxylic acid. The process of removal of a molecule of CO2 from carboxylic acid is called decarboxylation. When sodium salt of a monocarboxylic acid is fused with the soda lime formula for soda lime is NaOH per CaO in the ratio 3:1. At about 630 Kelvin, a molecule of CO2 is lost and an alkane with one carbon atom less than the carboxylic acid is formed. Sodium hydroxide alone could also have been used in the above reaction, but soda lime is preferred because of the following two reasons. It permits the reaction to be carried out at a relatively higher temperature to ensure complete decarboxylation. Second, CaO present in soda lime keeps it dry because NaOH is quite hygroscopic in nature. Limitation. Only sodium acetate gives a good yield of methane, while in all other cases such as decomposition of sodium propionate, butyrate and coprolate, a mixture product is obtained. Next reaction is called by electrolytic method. When a concentrated aqueous solution of sodium or potassium salt of lactic acid is electrolyzed, alkanes are produced. When this reaction is believed to occur through the following step. At a node, both carboxylate ion and OH negative ions will migrate towards the cathode. Since the electron releasing tendency of CH3 COO negative ion is much higher than that of hydroxide, and therefore CH3 COO negative ions will be discharged in the preference to OH negative ions. At anode, both Na positive and H positive ions will migrate towards the anode, since the electron accepting tendency of H positive ions is much higher than that of Na positive ions. Therefore, H positive ions will be discharged in the preference to Na positive ions. Thus, during Kolbe electrolysis, alkanes and CO2 will be evolved at the anode while H2 will be evolved at the cathode. Consequently, Na positive and OH negative ions will remain in the solution. In other words, as the Kolbe reaction proceeds, the pH of the solution gradually increases. Limitations of Kolbe's electrolysis. First is only alkanes with even number of carbon atom can be prepared by this method. Second is when a mixture of sodium or potassium salts of two different carboxylic acid is electrolyzed, a mixture of three alkane is produced, as we will already studied in that is the mixture of three is formed in always also in inverse reaction. Third is methane can't be prepared by this method. Next our topic is general physical properties. The physical properties of alkanes, such as melting point, boiling point, solubility, density, etc., mainly depend upon their intermolecular forces of attraction. Since alkanes are almost nonpolar molecules, therefore, the main attractive forces in them are van der Waals forces, which depend upon the shape and the size of the molecule. As the molecular size increases as we move down the homologous series, therefore, these properties show uniform variation down the family as discussed below. First, boiling point. The first four members C1, C4 among alkanes are colorless gases. The next 13 and alkanes means C5 to C17 are liquids, while the other members C18 onwards are waxy solids. The boiling point of straight chain alkanes increase fairly regularly with increase in their molecular mass. On the average, the boiling point generally increases by 20 to 30 Kelvin for the addition of each carbon atom or a CH2 group to a chain. The difference in boiling point is, however, greater for the lower homologous than for the higher homologous. This regular increase in the boiling point of straight chain alkanes with increase in the carbon content is due to corresponding increase in the molecular size and hence the surface area of the molecule. As a result, the magnitude of van der Waals forces of attraction goes up and hence the boiling point increase accordingly. Amongst isomeric alkenes, the branched chain isomer has invariably the lower boiling point from the corresponding alkene. This is due to the reason that with branching, the shape of the molecules tends to approach that of a sphere. As a result, the surface area of branched chain decreases. Due to lesser surface area of these molecules, the van der Waals forces of attraction operating between their molecules become comparatively weaker, and hence lesser amount of energy is required to overcome them. As a result, the boiling point of the branched chain isomer are lower than that of the corresponding alkenes. Further, it has been observed that greater the branching, lower is the melting point of the branched isomer. For example, the boiling point of 2,2-dimethyl propane with two branched is lower than that of 2-methyl butane with one branch chain and N-heptane with no branch chain. The melting point of a substance depends not only upon the size and the shape of the molecule but also upon how closely the molecules are packed in the crystal lattice. But due to sp3 hybridization in alkanes, any two bonds of carbon atom make an angle of 109 degree 28 minutes or inch with one another. As a result, in an alkane, the carbon atoms are arranged in zigzag chain rather than in a straight chain as commonly written. Therefore, in alkanes containing an even number of carbon atoms, the two terminal methyl groups lie on the opposite side of the zigzag chain. On the other hand, in case of n alkanes having odd number of carbon atoms, the two terminal methyl groups will lie on the same side of the zigzag chain. Thus, it is clear that N-alkanes with even number of carbon atoms are more symmetrical than containing odd number of carbon atoms and hence closely packed in the crystals. In other words, van der Waals forces of attraction are much higher in N-alkanes having even number of carbon atom than those having odd number of carbon atom. Therefore, N-alkanes with even number of carbon atoms have much higher melting point than that the next lower N-alkane with odd number of carbon atoms. For example, N-butane with even number of carbon atoms melts at 138 Kelvin, while the propane with three odd numbers of carbon atom melts in 85.3 kelvins. Similarly, n hexane melts at 179 Kelvin, while the lower alkane, that is n pentane, melts at 143.3 Kelvin. It may be noted that such an alternation effect is not observed in melting point, since in the liquid state the conformation of the molecules are not fixed but keep on changing as a result of collisions. Next property is solubility. Like dissolves like is the general rule of solubility. In the light of this, alkanes which are predominantly non-polar are soluble in polar solvents such as water, alcohol, etc., but are highly soluble in non-polar solvents such as petroleum, ether, benzene, carbon tetrachloride, etc. Fourth is density. The densities of alkanes increases with increase in the molecular mass till the limiting value of about 0.8 gram per centimeter cube is reached. This means all alkanes are lighter than water. Also, alkanes are paraffins. Paraffins means they are less reactive. Next, our topic is general chemical properties. Alkanes are a rather unreactive class of compounds. At room and moderate temperature, they are quite stable towards most of the chemical reagents such as acids, alkalis, oxidizing agent, reducing agents. The relative inertness of alkane is due to the following two reasons. First, alkanes are made up of only carbon and carbon and carbon hydrogen. Sigma bonds, which are non-polar since the electronegativities of carbon and hydrogen do not differ appreciably. Thus, alkanes are non-polar molecules. As a result, polar and ionic reagents find no reaction site in alkane molecules. Second is both carbon and CH bonds are quite strong. Therefore, collision of the alkane molecules with almost all the reagents at room temperature do not provide sufficient energy to break these bonds. However, at higher temperature or in the presence of UV rays, these collisions provide sufficient energy to break these bonds but only homolytically to produce free radicals. As a result, at high temperature or in the presence of ultraviolet light, alkanes undergo free radical reaction. The free radical reaction in principle can be either addition or substitution. Since alkanes do not contain multiple bonds, therefore only one type of reaction which only some type of reaction which alkanes undergo are free radical substitution reaction. Some important chemical reactions of alkanes are discussed under the following categories. First is substitution reaction, second isomerization reaction, third is alkylation reaction, fourth cracking or fermentation reaction, fifth is aromatization or reforming reaction, sixth is oxidizing agent. Now first is substitution reaction. In this reaction, one or two more hydrogens atoms of alkanes are replaced by an equal number of other atoms of group. Some important substitution reactions are halogenation, nitration and sulfonation. They are briefly discussed below. First is a chlorination. The most important substitution reaction of alkanes is called halogenation. It involves the replacement of one or more hydrogen atoms of an alkane by a corresponding number of halogen atoms. It is carried out by treating an alkane with a suitable halogen in the presence of UV rays or by heating the reaction mixture to 520 to 670 Kelvin. The order of reactivity of different halogen is fluorine is more reactive than chlorine, then corresponding to Br2 and then I2. Next is chlorination. During chlorination of methane, all the four hydrogen atoms are replaced by one to form a mixture of product. Third is bromination. Bromine reacts with alkanes in a similar manner but less radially. Fourth is iodine. The reaction of iodine with alkanes is reversible because the hydrogen iodide formed as a byproduct is moderate reducing agent and hence reduces the iodoalkanes back to alkene. This direct iodination of alkanes cannot be brought about. However, the addition can be carried out in the presence of an oxidizing agent such as iodic acid means HiO3 with nitric acid HNO3 or a mercuric oxide HCO which converts Hi to I2 and it is formed. Fourth is fluorination. Fluorination of alkanes is too vigorous to be controlled under ordinary conditions. Furthermore, fluorination brings about extensive rupture of carbon-carbon and carbon-hydrogen bonds leading to a mixture of products. This fluorination of alkanes with the pure fluorine is of little practical use. However, fluorination of alkanes can be carried out by diluting fluorine with an inert gas such as nitrogen or argon. Alternatively, alkyl fluorides are more conveniently prepared indirectly by heating suitable chloroalkanes with inorganic fluorides such as ASF3, SBF3, AGF, Hg2F2, etc. for example. This reaction is also called Schwarz reaction. Now next is nitration. The process of replacement of a hydrogen atom by a nitro group, that is NO2, is called nitration. At ordinary temperature, alkenes do not react with HNO3. However, when a mixture of alkane and fuming HNO3 vapors are heated at 423 to 673 Kelvin under pressure, alkanes undergo nitration, giving a mixture of nitroalkanes resulting through cleavage of carbon-carbon bond. Next is sulfonation. Substitution of hydrogen atom of alkane by sulfonic acid group, that is SO3H, is called sulfonation. It is carried out by heating an alkane with fuming sulfuric acid H2SO4 plus SO3 at 675 to 725 Kelvin. Branched chain and higher normal alkanes undergo sulfonation to give alkane sulfonic acid. The ease of substitution is tertiary, secondary, and then primary. So let's move further. Our next type of reaction is isomerization. When N-alkanes are heated with anhydrous aluminum chloride and hydrogen chloride, they are converted into branched chain alkanes. This process is called isomerization. The process of isomerization has been of great utility for increasing the octane number of carbon of a particular petroleum fraction mechanism. Isomerization occurs through carbocation intermediate, which results through the protonation of an alkene produced as a result of dehydrogenation of the alkene. The carbocation thus produced undergoes a series of 1,2-hydride or 1,2-methyl shift to produce a more stable tertiary carbocation, which ultimately accept a hydride ion from the alkene to produce the corresponding branched chain alkene. Next, our reaction is alkylation. Alkane containing a tertiary hydrogen atom such as isobutane react with alkene when heated in the presence of acid catalyst such as concentrated H2SO4 or HF to produce larger branched chain alkanes. For example, isobutane react with isobutylene in presence of concentrated H2SO4. It will produce 2,2,4 trimethylpentane. Our next reaction is cracking or fermentation. The process in which high boiling hydrocarbons are converted into a mixture of low boiling hydrocarbons by heating strongly in the absence of air is called cracking or fermentation. It involves cleavage of C and CH bonds and occurs via free radical mechanism. It is mainly of two types, terminal cracking and catalytic cracking. First is terminal cracking. It is cracking by the action of heat alone. Since during thermal cracking, random cleavage of carbon-carbon bond occurs. Therefore, cracking of dodecane can give a number of hydrocarbons such as decane, nonane, octane, heptane, hexane, pentane, butane, propene, butene, pentene, hexene, etc. Thus, from the above discussion, we conclude that that thermal cracking is difficult to control and hence a complex mixture of product is always obtained. It is because of this limitation that nowadays cracking is used instead of thermal cracking. Now let's read cracking. Catalytic cracking is in fact thermal cracking in presence of a catalyst. The most commonly used catalyst is a mixture of silica and alumina in the ratio 4:1. Catalytic cracking is generally carried out at low temperature up to 600 to 650 Kelvin than thermal cracking. This is most widely used method in the petroleum industry and at present about 85% of the total world production of gasoline is obtained by this method. Further, this is the important method for the manufacturing of alkenes such as ethene, propene and butene which are widely used in the industries. Next is aromatization or reforming. An alkene containing 6 to 8 carbon atoms which heated to 873 Kelvin under pressure of 10 to 20 atmospheric and in the presence of a catalyst consisting of oxides of chromium, molybdenum and vanadium supported over alumina are converted into aromatic hydrocarbons. Other catalysts which are commonly used is palladium, platinum, or nickel. The process which involves cyclination, isomerization, and dehydrogenation is called aromatization and is widely used for the manufacturing of aromatic hydrocarbons such as benzene, toluene, xylenes, etc. from N-alkanes and cycloalkanes. In petroleum industry, this process is used to improve the quality of gasoline. Therefore, it is called reforming. Further, it has been found that platinum is the most and best catalyst, and that is why reforming is sometimes referred as a platforming. Next and last reaction is oxidation reaction. Some important reactions of alkanes are as follows. First, complete oxidation reaction or combustion. On heating, alkanes readily burn in air oxygen producing CO2 and H2O. This process is called combustion. Since the process of combustion is accompanied by the liberation of large amount of heat, therefore alkanes, which are substituents of LPG, gasoline, kerosene oil, and diesels, are widely used as fuels. Second is incomplete combustion. If the combustion of alkanes is carried out in limited supply of air or oxygen, CO is produced along with unburned carbon in the form of carbon black or soot. Carbon black is used in the preparation of a black inks, paints, polishes, etc. Second is reaction with steam. Methane reacts with steam at 1273 Kelvin and the presence of nickel as a catalyst, forming CO and H2. This method is used for industrial preparation of dihydrogen. Next is catalytic or controlled oxidation. Different products are formed under different conditions. First, when a mixture of methane and oxygen in the ratio 9 by 1 by volume at a pressure of 100 atmosphere, it passed through a copper tube at 573 methane is formed. Second, when a mixture of methane and oxygen under pressure is passed over heated molybdenum oxide, it is oxidized to methanol. Third, higher alkanes on oxidation in the presence of silver oxide give carboxylic acid. Fourth, in general, oxidizing agents such as KMnO4, K2Cr2O7, etc. have no effect on alkanes. However, alkanes containing a tertiary hydrogen can be oxidized to the corresponding alcohols. Now our next topic is relative reactivities of halogen in the halogenation of alkanes. We have already stated that the relative reactivities of various halogen towards halogenation of alkanes follow the sequence F2, then Cl2, then Br2, and then I2. This order of reactivity can be easily explained on the basis of magnitude and the sign of H of these halogenation reactions as below. It follows from the above values of delta H that fluorination, chlorination, and bromination are exothermic reaction, while iodination is endothermic. Further, since the value of delta H decreases from fluorine to chlorination and then to bromination, it follows that the order of relativity of methane towards halogenation is F2, followed by Cl2, Br2, and I2. We have already studied that each of the above halogenation reaction consists of three steps. Let us now examine as to which of these steps in fact determine the order of the reactivity. Step 1. A simple dissociation reaction and hence delta H is equals to E of activation. Chlorine with the highest activation energy, that is 242.5 kJ per mole, should dissociate most slowly, while iodine with the lowest activation, that is 150.5 kJ per mole, should dissociate most rapidly. But this order of reactivity does not agree with the experimental fact. Therefore, step 1 can't control the order of reactivity of different halogen and the halogenation of the alkanes. Next is step seconds, involving the abstraction of hydrogen from methane by a halogen atom has a wide spread of delta H values. For exothermic reaction, E activation can be very small, but for endothermic reaction, it has to be at least as large as delta H for the reaction. Experimentally, it has been found that for the highly exothermic reaction with fluorine atom, E activation energy for step 2 is just 4.18 kilojoule. For the slightly endothermic reaction with chlorine atom, it is 16.72 kJ, and for moderate endothermic reaction with bromine atom is 75.24 kJ, and for the highly endothermic reaction with the iodine atom, activation for step 2 has to be at least as high as 137.9 kJ. In other words, a decreasing order of activation for step 2 for the other halogen. 4 halogen is iodination followed by bromine, chlorination and fluorination. Consequently, the order of reactivity of the various halogens towards methane should follow the sequence: fluorination, chlorination, bromination, and iodination. Thus, step 2 controls the reactivity of the various halogens towards halogenation of methane and alkanes as well. Now let's move further. Our second part is cycloalkanes. Introduction. Aliphatic cyclic compounds are called alicyclic. Ali from aliphatic and cyclic from their ring structure compounds. These compounds are so named because they resemble aliphatic compounds in most of their properties but possess cyclic structures. However, due to their cyclic nature, they differ from aliphatic compounds in some respects. Alis- Alicyclic compounds are also called carboxylic compounds since their rings are made up of only carbon atoms. Like open chain hydrocarbons, alicyclic compounds can also be saturated or unsaturated. Saturated alicyclic compounds corresponding to alkanes or paraffins are called cycloalkanes or cycloparaffins. Those corresponding to alkenes are called cycloalkanes, while those corresponding to alkyls are called cycloalkynes. In this unit, we shall discuss the nomenclature, general method of preparation, chemical properties, and the effect of ring on the relative stabilities of the cycloalkanes. Next is nomenclature. The general formula of cycloalkane is CnH2n or CH2 bracket close n, where n is equals to 3, 4, 5 up to and so on. Since alkanes are represented by the same general formula, therefore cycloalkanes are isomeric with alkenes. Further, since in these compounds a number of methylene units are joined together to form a ring, they are also called polymethylens. The name of any saturated alicyclic hydrocarbon is then obtained by attaching the prefix tri, tetra, penta, hexa, etc. of the word methylene according as the number of carbon atoms in the ring as 3, 4, 5, 6, etc. respectively. In the IUPAC system, the saturated alicyclic hydrocarbons are called cycloalkanes. The name of an individual cycloalkane is obtained by prefixing the word cyclo to the name of the corresponding alkane having the same number of carbon atoms as the ring. For convenience, alicyclic compounds are usually represented by simple geometric figures are also called polygon formula, that is a triangle for cyclopropane, a square for cyclobutane, a pentagon for cyclopentane, hexagon for cyclohexane, and so on. In such representation, it is understood that each corner represents a CH2 group unless some other substituent is indicated. Now next is IUPAC name of the substituted alkenes. The following rules are generally followed first. In case of the substituent cycloalkanes, the numbering of the ring carbon atom is done in such a way that the substituent get the lower number. The name of the substituted alcohol is then obtained by prefixing the name of the substituent to the name of the parent cycloalkane. In case there is more than one substitution, each substitution prefixed by its loctant is arranged in alphabetically order before the name of the parent alkene. Second point is if the ring contain more or equal number of carbon atom than the alkyl group attached to it. If it named as a derivative of cycloalkane and the alkyl group is treated as a substituent group, otherwise it is named as a derivative of alkane and cycloalkyl group is considered as a substituent. Now our third rule, if multiple bond and some other substituents are present in the ring, the numbering is done in such a way that the carbon atom of the multiple bond get lower loctants 1 and 2 and the substituent group get the lower loctant at their point of difference. Fourth, if ring contains a multiple bond and the side chain contains a functional group, then the ring is treated as a substituent and the compound is named as a derivative of the side chain. Now next fifth rule is if the ring as well as the side chain contain functional group, the compound is named as a derivative of the side chain or the alicyclic cyclic ring according as the side chain or the ring contains the principal functional group. Sixth, if a compound contain an alicylic ring directly linked to the benzene ring, it is named as a derivative of benzene, that is, the compound having lowest state of hydrogenation. Seventh, If some functional group along with other substituent groups are present in the ring, it is indicated by some appropriate prefix or suffix, and its position is indicated by numbering of the carbon atom of the ring in such a way that the functional group gets the lower number. Eighth and last rule is if an alicyclic contain carbon containing functional group, the carbon atoms of the functional group are not included in the parent name of the cyclic system. Therefore, for such system, the following prefix and suffix for the functional group are commonly used. Now our next topic is synthesis of cycloalkanes and their derivatives. Some important general method of synthesis of cycloalkanes and their derivatives are discussed below. First, cycloaddition reaction. An addition reaction between two unsaturated components leading to the formation of a cyclic product are called cycloaddition reaction. In this reaction, the pi electrons of the two components form two new bonds. These reactions are usually designated by writing the pi electron of the two components, usually in the descending order, separated by a plus sign in the square bracket. For example, 2 plus 2, 4 plus 2, 6 plus 4, cycloaddition reaction. For example, 2 plus 2 cycloaddition involves addition of two alkenes molecules to form a cyclobutane derivative. These reactions do not involve ionic or free radical intermediate and occur in a single step via cyclic transition state in which the bond making and bond breaking occur simultaneously. Such concentrated reactions which occur through cyclic transition state are called pericyclic reactions. These reactions do not require any catalyst and they are initiated either by heat or light. The following cycloaddition reaction can be used to prepare cycloalkanes. First, 2 plus 2 cycloaddition reaction. This cycloaddition reaction can be used to prepare both cyclobutane and cyclopropane derivative as discussed below. First, synthesis of cyclobutane derivative. One of the most important methods for the synthesis of cyclobutane derivative involves the addition of two molecules of the same, means dimerization or different alkenes. These reactions generally occur under photochemical condition by a concentrated mechanism via a cyclic transition state. In case of substituted alkene, although the addition takes place on the same phase of the alkene, yet the two molecules of alkene may approach each other in two different ways, giving a mixture of two products. Similarly, trans-2-butane on photochemical dimerization gives a mixture of two products, cis, cis and anti and cis anti-cis and all trans tetramethyl. It may be here noted that substituted alkenes containing electron withdrawing substituents such as fluorine, COR, cyanide, carboxylate, etc. form cyclobutane derivative under thermal conditions. These reactions proceed via a free radical mechanism involving diradical intermediate. Let's move to second method, that is synthesis of cyclopropane derivative. Another example of 2 plus 2 cycloaddition reaction involves the addition of the free carbene or carbenoids to alkene to give cyclopropane derivative. First, addition of free carbenes. Photolysis of dimethane in the presence of propene first gives methylene, a free carbene, which then adds to propene to give methyl cyclopropane. Thus, Methyl itself, methylene itself is very reactive and hence give many side reactions, especially insertion reaction, which greatly reduce the yield of the cycloaddition reaction. Halocarbenes, on the other hand, being less reactive than methylene, do not undergo insertion reaction and hence give good yield of cycloaddition. For example, cyclohexane in the presence of CCl2 or CH3, CH3COK gives 7,7 bicyclo, or we can say 4,10 heptane in the presence of in 59% the product is. Next is addition of carbenoid or Simon-Smith reaction. Addition of methylene to alkene give low yield of cyclopropane derivatives since it being extremely reactive undergo many side reactions, especially insertion reaction. Therefore, when it is desired to add CH2 for preparative purposes, free carbene is not used. Instead, a carbene-like species called the carbenoid is used, which generally improves the yield of the cycloaddition product by reducing the insertion reaction. One such reaction is called Simmons-Smith reaction, which uses diiodomethane in the presence of zinc copper couple as a source of carbon like species. The addition in stereospecifically sin and occurs by a concentrated mechanism as given below. Third is second is 4 plus 2 cycloaddition reaction. This reaction is also called Diels-Alder reaction. This reaction involves the addition of an alkene or alkyne molecule called the dinucleophile to a conjugated diene, resulting in the formation of six-membered ring. For example, cyclohexane is obtained by heating a mixture of butadiene and ethylene at 475 Kelvin. The Diels-Alder reaction does not require any catalyst. The two components are either heated together or heated in some solvent such as benzene, toluene, chlorobenzene, etc. If the dinucleophile contains an electron withdrawing group such as CO, CHO, CO2H, CO2R, anhydride quinone, etc., the reaction can be carried out at a much lower temperature. Further, greater the number of such electron withdrawing groups, more reactive is the dinucleophile. Thus in Diels-Alder reaction, maleic anhydride is a useful dinucleophile, while tetracyanomethylen is the most reactive dinucleophile discovered so far. Other useful dienes are isopropane, means 2-methyl 1,3, butadiene, and cyclopentadiene. Stereochemistry. Diel-Alder reaction is a stereospecific cis addition reaction. That is, stereochemistry of the dinucleophile is retained in the product. For example, if the diene is cyclic, two cis addition products are possible. They are called endo and exoadducts. In the endoadduct, the molecule of the dinucleophile lies underneath the diene component, but in the exoadduct, the two components project away from each other. The example is situated below. It may be here noted that the Diels-Alder reaction, it is thermodynamically less stable endo product which always predominates over the most stable exoadduct. Now our second reaction is dehalogenation or alpha gamma dihaloalkanes Freund's method. This method involves the action of active metals such as zinc, sodium on suitable alpha gamma dihaloalkanes. This reaction may be regarded as an intermolecular Wurtz reaction. This reaction gives good yield of only cyclopropane. Next, our reaction is Dickerman cyclization or condensation. Esters of alpha gamma dicarboxylic acid undergo intermolecular condensation called Dickerman cyclization or condensation in the presence of molecular sodium dust or sodium methoxide to form cyclic beta ketoesters. These cyclic beta ketoesters on substituent hydrolysis and decarboxylation yield cycloalkane, which can be converted to the corresponding cycloalkanes by Clemenson reduction. For example, cyclopentane can be synthesized from diethyl adipate by the following sequence of the reaction. Next, our reaction is hydrolysis of 2-carboethoxycyclopropane to 2-carboxyl cyclopentanone. This is the usual acidic hydrolysis of an ester to the corresponding carboxylic acid, and it is achieved by heating the ester with dilute HCl or H2SO4. Third reaction is decarboxylation of 2-carboxycyclopentane to cyclopentanone. Since 2-carboxycyclopentanone is a beta keto acid, it readily undergoes decarboxylation on heating to give cyclopentanone. Fourth reaction is reduction of cyclopentanone to cyclopentane. The inversion of the cyclopentanone to cyclopentane is conventionally achieved by Clemenson reduction. Similarly, Dickerman cyclization can be used to prepare cyclohexane from diethylprimylate. Fourth reaction is pyrolysis of calcium and barium salt of decarboxylic acid. This reaction is also called Wieslinius method. Calcium, barium, or thorium salts of dicarboxylic acid yield cycloalkanones on heating, which can be readily reduced to the corresponding alkanes by Clemenson reduction. In accordance with the Planck rule, this method gives good yield for 5-6 membered rings. Planck rule. The effect of heat on carboxylic acid can be summarized in the form of blank rule, which states that carboxylic acid in which the two carboxyl group are attached to the same carbon, that is 1,3-dicarboxylic acid, upon heating undergo decarboxylation to form monocarboxylic acid. Second, 1,4 and 1,5 dicarboxylic acid on heating alone or upon distillation with acetic anhydride form cyclic anhydride. Third, 1,6 and 1,7 dicarboxylic acid on heating alone or upon distillation with acetic anhydride give cyclic ketones with the loss of one carbon atom as carbon dioxide, while 1,8 and higher dicarboxylic acid remains unaffected. There are some examples of this below. This rule is quite useful in determining the ring size of a cyclic compound. For this purpose, a double bond is introduced into the ring by some unknown method. The ring is then oxidized with the help of KMnO4 to give dicarboxylic acid, the pyrolysis of which helpful us to determine the size of the ring. Now our fifth reaction is Thorpe-Ziegler reaction. This is the best method for preparing a large macrocyclic ring in good yields. It consists of treating an alpha in which the nitrile group add the terminal carbon atom with a base such as lithium diethylamide, commonly abbreviated as LDA or lithium ethyl phenylamide in the benzene or toluene. The dinitrile undergo an intermolecular condensation called Thorpe reaction to form a cyclic beta aminonitrile, which upon hydrolysis give the corresponding cyclic ketone in good yield. The cyclic ketones can then be reduced by elimination method to give the corresponding cycloalkanes. Like Dickman cyclization, this reaction also gives good yield of only for 5 or 6 membered rings. However, by using Ziegler high dilution technique, macrocyclic rings have been prepared in good yield. In this technique, a very dilute solution of the dinitrile is nitrile in benches is added to the solution of basic catalyst in large excess of ether. This ensures intermolecular reaction by considerably reducing the intermolecular reactions. In this way, yields of 95% of 7-membered ring, 86% of 8-membered, 60 to 80 rings with 14 or more carbons have been obtained. Yield of 9 to 13 membered rings are, however, less than 15. Now our next topic is general physical properties. Cycloalkanes closely resemble their open chain analogues, that is alkanes, in their physical properties, although their melting point, boiling point and densities are somewhat higher. This is probably due to the reason that zigzag alkanes molecules are constantly oscillating and hence they cannot be closely packed in the crystal lattice. On the other hand, cycloalkanes, because of their rigid ring structure, overcome this oscillation to a great extent and hence they are comparatively more closely packed. This closer packing results in a strong intermolecular forces, that is van der Waal of attraction, and hence cycloalkanes have higher melting point than the corresponding alkanes. In liquid state also the cycloalkane molecule are a little more strongly held and hence have higher boiling point than corresponding alkanes. Further, because of close packing, cycloalkanes have higher densities than corresponding alkanes. Like alkanes, cycloalkanes are nonpolar molecules and hence are soluble in nonpolar solvents such as carbon tetrachloride, petroleum, ether, etc., but are insoluble in polar solvents such as water, alcohol, etc. Now, next is general chemical properties. The general formula of the cycloalkanes CnH2n suggests that they should be unsaturated, and hence should resemble alkanes. Now we will do general chemical properties of the cycloalkanes. First is free radical substitution reaction. Cycloalkanes undergo the typical free radical substitution reaction when treated with halogens at 525 to 575 in the dark or room temperature in the presence of light. Second is addition reaction. As discussed above, like alkanes, cyclopropane undergo addition reaction. Some of the important reactions are given below. However, unlike alkenes, cyclopropane does not add ozone and also does not undergo hydroxylation with aqueous KMnO4 solution. Cyclobutane, on the other hand, is less reactive than cyclopropane and does not undergo addition reaction under ordinary condition. However, on hydrogenation at higher temperature, it gives N-butane. Now, question arises as how to account for this special behavior of 3 or 4 membered ring. Now we will do the Bayes chain theory and relative stability of the cycloalkanes. To explain the relative stability of cycloalkanes and the exceptional behavior of 3 or 4 membered rings, Adolf von Baer in 1885 proposed a theory known after his name, Bayes chain theory. The main postulates of these theories are given below. A carbon atom bonded to a four other atoms is tetrahedral. That is, the angle between any pair of two adjacent bonds is tetrahedral. That is 109 degree 28 minutes. All the carbon atom constituting a cycloalkane molecule lie in a plane. As a result, the bond angles between any two adjacent carbon atoms are no longer equal to the normal tetrahedral angle. They are either less or more than this angle. Any deviation or distortion from this normal tetrahedral angle imparts strain and hence instability to the resultant molecule. The strain is commonly referred to as the angle of strain. The greater the deviation from the normal tetrahedral angle, greater is the angle strain and hence greater is the instability of the resultant molecule. The greater the stability of a ring system, more easily is formed. The extent of angle strain introduced depends upon the size of the ring. In order to explain the relative stability of different cycloalkanes, let us determine the magnitude of the angle strain in each of them with the following expression. Angle of strain is equals to 1 by 2 109 degree 28 minutes minus bond angle in the planar ring. Now we will calculate the angle of strain for the cyclopropane. 1 by 2 109 degree 28 minutes minus the angle between the two planar rings in the cyclopropane is 60 degree. So we will get, after solving this calculation, we will get the angle of strain, that is 24 degree 44 minutes. And for similarly we will calculate the cyclobutane and it is of 90. Now we will get 9 degree 44 seconds. Okay, the positive value of angle strain indicates that the bond length are corresponding, while negative value means expansion of the bond angles from the tetrahedral angle. In both the cases, the molecules will be strained. In other words, it is the magnitude of the angle strain and it is not, it's a sign which determines the strain and hence the instability of the molecules. Evidence in support to Bayes strain theory. First, reactivity of the double bond. A double bond may be regarded as a two-membered ring with a carbon-carbon bond angle of 0 degree. Therefore, the angle of strain is 54 plus 54 point degree 44 minutes. Since the angle strain is highest for all the cycloalkanes, hence the alkane should be highly reactive, and which is in the agreement with the observed fact. Second is reactivity of cyclopropane and cyclobutane. A comparison of the heats of the combustion and cycloalkanes reveals that cyclopropane and cyclobutane possess more energy per CH2 group than the corresponding straight chain alkanes. Consequently, they should be less stable than the corresponding analkanes. A fact in agreement with the Bayes strain theory. It is therefore reasonable to believe that their tendency to undergo addition reaction through ring fission is related to their instability. Next, we will do the limitations of Bayes strain theory. Some of the limitations of the Bayes strain theory are as follows. On the basis of Bayes strain theory, a carbon-carbon double bond should be difficult to form since it is highly reactive and highly unstable. In contrast, it is known fact that a carbon-carbon double bond is easily formed by dehydrogenation of alkyl halides, dehydration of alcohols, etc. Second, on the basis of Bayes strain theory, cyclohexane in rings having 7 or more carbon atoms should be less stable than cyclopentane. But heat of combustion data reveals that cyclopentane, cyclohexane, and ring containing 7 or more than carbon atoms are equally stable. Now, our next and last topic of this chapter is Shas-Mohr theory of stainless rings. As discussed above, Bayes' theory could not explain the stability of the rings containing 5 or less carbon atoms but failed to account for the stability of rings containing 6 or more carbon atoms. To account for the stability of 6-membered and larger rings, Schacht and Mohr examined the model of cycloalkanes and proposed the theory of stainless rings. According to this theory, the carbon atoms of a 5-membered and smaller rings can be in single plane and postulated by Bayer, but in 6-membered and larger than they lie in a different plane. In other words, the ring containing 5 or less carbon atoms are either planar or very nearly planar, but those of 6 or and more carbon atoms are essentially non-planar or puckered. As a result of this puckering, each carbon atom retains its normal tetrahedral angle and there is negligible or no strain in the molecule. In other words, 6-membered and larger rings are strainless and hence the name theory of the stainless rings. Further, Schesch and Mohr were able to construct the model of two puckered forms of cyclohexane called the boat and the chair form. These forms of cyclohexane are readily interconvertible by rotation about single bond and and hence represent the conformations of cyclohexane. Similarly, Similarly, rings larger than 6 carbon atoms can negligible angle strain by assuming puckered arrangement of the atoms in their molecules. Now the question arises, if the large rings are stable, why they are difficult to synthesize? Bayes' assumption that a compound difficult to synthesize, it's necessarily unstable is not correct. Actually, for ring closure to occur, it is essential that the two ends of the carbon chain possessing the functional group must come sufficiently sufficiently close together to react with other molecules. Evidently, larger the ring to be synthesized, larger must be the chain from which it is made, and hence less is the likelihood of the two ends of the same chain approaching each other. Under these conditions, there would be greater probability for the two different chain chains coupling together rather than the two ends of the same chain undergoing ring closure, that is intermolecular condensation. Thus, the difficulty encountered in the synthesis of the large membered ring in the competition between inter and intramolecular condensation, with the former predominating. However, recently this difficulty has been overcome by carrying out the reaction in highly dilute solution. Under these conditions, the collisions between the two different chains are minimized considerably, and the ring closing reactions, although slow, is the principal reaction. Now we will do the case of the cyclopropane, that is banana bonds. Cyclopropane offers an interesting case of bent cis covalent bond. It is planar molecular and an internal bond angle must of 60 degrees. Therefore, there is a considerable deviation from the tetrahedral angle, but carbon cannot hybridized orbitals oriented at an angle less than 90 degrees to each other. Since there are four bonds on each other, therefore the angle have to be more than 90 degrees. In other words, in cyclopropane, the ring pi bonds cannot be formed by overlap of pure orbitals. To explain this ambiguity, it has been shown that the hybridization of orbitals occur in such a way that the ring forming orbitals have a slightly greater p character than those forming the normal sigma bonds between carbon atoms in saturated molecules. This explains why the angle phi between two such orbitals of one carbon atom in cyclopropane is 104, little less than the tetrahedral angle of 109 degree 28 minutes. Thus, the measure excess of symmetry of the orbitals forming cis carbon-carbon bond in cyclopropane do not point towards one another but outwards from the molecule with the appearance of the bananas. It is because of this reason the carbon-carbon bond in cyclopropane are offered as a bent or banana bonds. Further, due to higher p character of the hybridized orbital, there is a small but appreciable pi delocalization around the ring. However, delocalization occurs within the plane of the ring and not above and below the carbon framework of the aromatic system. Thus, in plane, pi delocalization adds some stability to the ring structure. That is the chapter alkanes and cycloalkanes. Now, today is for that. Thank you and have a cheerful day.